Ever wondered what makes mothballs have their distinct smell? It's a polycyclic compound known as naphthalene. Welcome to the intriguing world of polycyclic compounds, a fascinating corner of chemistry that often goes unnoticed despite its ubiquitous presence in our daily lives. These compounds, made up of two or more fused aromatic rings, are like the unsung heroes of the chemical world, quietly playing pivotal roles in a variety of applications. From the mothballs that keep your clothes moth-free to the vibrant dyes that color our world, polycyclic compounds are everywhere. In fact, they're even present in the DNA that defines who we are, in the form of purines and pyrimidines. But what exactly are these polycyclic compounds? Well, as the name suggests, these are organic compounds containing closed rings of atoms. Picture a collection of rings, each one connected to another, creating a complex and intricate structure. Each ring is aromatic, meaning it has a special type of stability due to a phenomenon known as resonance. And here's where it gets even more interesting. These compounds, despite their structural complexity, follow simple and predictable rules when it comes to their reactions. This predictability is a blessing for chemists, allowing them to manipulate these compounds in creative ways, leading to the synthesis of a myriad of useful substances. However, it's not all rosy with polycyclic compounds. Some of them, like polycyclic aromatic hydrocarbons, are known to be environmental pollutants, and are even linked to health issues like cancer. This dual nature of polycyclic compounds, their utility on one hand and potential harm on the other, makes them a fascinating subject of study. In the world of chemistry, understanding is the first step towards mastery. Now that we understand what polycyclic compounds are, let's dive into the synthesis and reaction of a few significant ones. Together, we'll explore naphthalene, the compound responsible for the distinctive smell of mothballs, phenanthrene, and anthracene. So, buckle up for a fascinating journey into the world of polycyclic compounds. Naphthalene, the main ingredient in traditional mothballs, is a polycyclic aromatic hydrocarbon. But how does it form, you may ask? Let's embark on a journey to unravel this chemical mystery. The synthesis of naphthalene can be accomplished in two major ways. The first method involves acetylene, a compound you might recognize from welding. In this process, acetylene units are joined together in a series of reactions to form the naphthalene molecule. This is a complex process involving several steps and a lot of heat. Alternatively, naphthalene can be synthesized from benzene. This process is more commonly used due to the abundance of benzene. In this reaction, two benzene molecules undergo a reaction known as alkylation, where one hydrogen atom from each benzene is replaced by a methyl group. The resulting compound, known as dimethylbenzene, then undergoes a process called dehydrogenation, where hydrogen atoms are removed and a double bond forms. This process is repeated, creating a second ring, and voila, we have naphthalene. But the story doesn't end with the synthesis of naphthalene. This versatile compound is also known for its reactions such as oxidation, nitration, and sulfonation. In oxidation, naphthalene reacts with oxygen in the air to form phthalic anhydride, a compound used in the production of plastics. On the other hand, in nitration, naphthalene reacts with nitric acid to form nitronaphthalene, a compound used in the production of dyes. Lastly, in sulfonation, naphthalene reacts with sulfuric acid to form sulfonic acid, a key component in the manufacture of detergents. Each of these reactions showcases the versatility of naphthalene and its important role in the chemical industry. From mothballs to plastics, dyes, and detergents, naphthalene's reach is far and wide. So next time you smell a mothball, remember the fascinating chemistry behind naphthalene. It's not just a simple compound, but a marvel of chemical synthesis and reactivity. Phenanthrene, another polycyclic aromatic hydrocarbon, is less common but equally interesting. This intriguing compound, composed of three fused benzene rings, has a unique resonance structure that contributes to its stability. Now, let's dive into the synthesis of phenanthrene. It's typically derived from naphthalene or anthracene, two of its polycyclic aromatic cousins. From naphthalene, phenanthrene is synthesized through a series of steps including sulfonation, nitration, reduction, and cyclization. The process is a perfect illustration of the beauty of organic chemistry, where a series of reactions can transform one molecule into another. When starting from anthracene, the synthesis of phenanthrene involves the intriguing Diels-Alder reaction. This reaction, named after its discoverers, Otto Diels and Kurt Alder, is a beautiful example of a paracyclic reaction where bonds are broken and formed in a cyclic manner. In the case of phenanthrene, anthracene reacts with maleic anhydride under heat, forming a Diels-Alder adduct, which upon further heating undergoes a retro-Diels-Alder reaction to yield phenanthrene. As for its reactions, phenanthrene primarily undergoes oxidation reactions. When oxidized, phenanthrene forms phenanthronequinone, a compound with two carbonyl groups. This reaction is a classic example of how polycyclic aromatic hydrocarbons can be transformed into more complex compounds, illustrating the versatility of these molecules in organic chemistry. But it's not just about the chemistry. Phenanthrene also finds its use in the manufacture of dyes and drugs, showing that the impact of these compounds stretches beyond the laboratory and into everyday life. So there you have it. Phenanthrene might not be as familiar as naphthalene, but its chemistry is equally intriguing. From its synthesis from naphthalene or anthracene to its oxidation reactions, phenanthrene is a testament to the beauty and complexity of polycyclic aromatic hydrocarbons. Stay tuned for more on the fascinating world of these compounds. Finally, let's explore anthracene, a key ingredient in the production of red dye. Anthracene is a polycyclic aromatic hydrocarbon, a molecule composed of 3 fused benzene rings arranged in a linear fashion. It's a fascinating compound that's not only found in coal tar, but also in the universe's infinite expanse detected in the interstellar medium. Let's delve into the synthesis of anthracene. It can be synthesized from benzene or phenanthrene. From benzene, anthracene is synthesized through a series of reactions involving Friedel-Crafts acylation, followed by cyclization and dehydrogenation. When starting with phenanthrene, anthracene is obtained by a simple isomerization process, where the angular hydrogen atom is removed and added to a different location, altering the structure and hence the properties of the compound. Now, onto its reactions. Anthracene undergoes several fascinating reactions, including oxidation and the Diels-Alder reaction. Oxidation of anthracene, particularly with chromic acid, yields anthraquinone, a compound used in the production of dyes and pigments. The Diels-Alder reaction, on the other hand, is a paracyclic reaction that forms 6-membered rings. Anthracene acts as a DNA in this reaction, combining with a dienophile to form a new ring structure. This reaction is particularly important in the synthesis of a variety of complex organic compounds. The chemistry of anthracene doesn't stop at laboratory reactions. It has a significant role in various industrial applications. With its ability to fluoresce under ultraviolet light, anthracene is used in the manufacture of certain types of dyes and pigments. It's also used in the production of certain plastics and in the development of organic semiconductors. Anthracene's chemistry is crucial in many industrial applications, including dye manufacturing. From its synthesis to its reactions and applications, anthracene is a fascinating compound, a testament to the intricate and captivating world of polycyclic aromatic hydrocarbons. Polycyclic compounds such as naphthalene, phenanthrene, and anthracene play significant roles in our lives and in various industries. We've journeyed through a fascinating world today, delving deep into the synthesis and reactions of these intriguing compounds. Let's take a moment to recap the key takeaways from our exploration. We started our journey with naphthalene, a polycyclic aromatic hydrocarbon composed of 2 fused benzene rings. We learned about its synthesis through the Haworth reaction, its reactions such as sulfonation, nitration, and halogenation, and its wide-ranging applications in industries such as agrochemicals, detergents, and pharmaceuticals. Then, we moved on to phenanthrene, a lesser-known but equally fascinating compound. Its synthesis via the Elb's persulfate oxidation and its reactions like oxidation and Diels-Alder reactions were discussed. We also highlighted its use in research and pharmaceuticals, underlining how these compounds touch various aspects of our lives. Finally, we unveiled anthracene, an aromatic hydrocarbon consisting of 3 fused benzene rings. Its synthesis via the Diels-Alder reaction and its reactions, such as oxidation and reduction, were explored. We also touched on its role in the production of dyes and the manufacturing of certain types of plastics, illustrating the wide-ranging impact of these compounds. Throughout our journey, we've seen how these polycyclic compounds, while complex, have practical applications that impact our daily lives. From the clothes we wear to the medicines we take, these compounds are integral to many aspects of our lives, and that's just the tip of the iceberg. There's a whole world of polycyclic compounds out there waiting to be explored, each with its unique properties and applications. So, there you have it, a journey through the fascinating world of polycyclic compounds. Subscribe for more because you won't find me later.